Hi everyone, we're on the home page of the phet.colorado.edu, a simulation platform for science and mathematics education. In this website we have over 806 million simulations delivered up to date, and today we shall be looking at how we can actually make use of this simulation to achieve light and color experiment, especially in the aspect of reflection and refraction. So very quickly, I go to the physics aspect of this simulation, and on the physics aspects, I am very much interested in going to light and radiation. So I will unselect all other category, then I will pick light and radiation. So under light and radiation, I'm going for bending light. Bending light is an HTML5 simulation app, meaning it can be run by any modern day browser, and it can actually be run offline, so you don't have to be on the internet for you to make use of this simulation app. Once you download it once and for all, you can go ahead and use it as many times as possible. So to download the bending light simulation app, I click this place and I have it downloaded as .html file, which can be used offline anytime, any day. So my file is downloaded. It's a very small file, about 2.0 megabyte file. So I go to the location where this is located and I simply double click it. Then I have my simulation running directly on my C. So you can see this is actually running on my local drive C. Okay, so we have three parts in this simulation. The first part is the intro part, we have the Prisms part, and then we have more tools part. We'll actually be working on this more tools. So I quickly take a quick intro to show you what all this looks like. So we have a source of light here, which when this red button is pressed, you have an incident ray of light being incident from a medium to another medium. In this case, to the extreme right of this page, you can see we have the first material here is air, and then the second material here is water. If we click this arrow, we can actually see that we can change this medium to any other medium of a choice. Then instead of using ray of light, we can as well use wave. Of course, we're going to get the same thing. Then we have a protractor here, and we have a meter that can measure intensity by this side of this. So we go to the next one, which is prisms. I can go to prism from this part, and so under prism, as usual, we have a source of light here, which can also be varied to just incident or beam of light, so you can see here, or you can even have this. So depending on the experiment of interest, the environment can also be varied. Okay, and then the intensity of light can also be varied from between 380 nanometer to as much as 700 nanometer. Okay, so the wavelengths of the radiation can also be varied as desired. Then we have different type of prisms here. We have the triangular prism, we have a trapezoidal, we have rectangular, we have a circular, we have semicircle, and so on and so forth. And this prism can also be assumed to be glass, or can be changed to different other materials. Okay, when this experiment is being conducted, we can also show different tools that are relevant to this experiment. For instance, if I bring this here, if I bring a triangular prism here, you can see what we have got. Okay, so let's show our normal. That's normal, and then we can show the reflected rays of light. Okay, so quickly we go to the final part, which is more tools. Okay, so here I believe most of the tools available here are what we have seen in the intro and in the present. This is source of light as usual, and the angle of incident can actually be varied by simply clicking and then moving this incident light source. Okay, the frequency or the wavelength of the ray can also be varied as desired. So as of now we have 650 nanometer. Okay, now we have also the medium. From here we have air as our medium where the incident light is coming from, and then we have glass as the medium receiving the incident light. Okay, and as we all know, the refractive index of glass is 1.5. So we can simply set up a simple experiment where students can be asked to vary the incident angle from, say, maybe 30 to 60 or 65, and then record the refracted angle, as we will see shortly. So in doing that, I need to show all this, and then as we can see, so as it is, this is my incident angle for this incident ray. My incident ray progressed from this source of light, and at the interface between air and glass we have the refracted ray, and it's refracted at angle 20.4 when it is incident at angle 31.6. Let me go to incident angle of, say, 30. I have to go up, and when this green arrow shows, that's when I can actually move this. So okay, so I have 30 degree. Okay, so when my incident angle is at 30 degree, I have my refracted angle being refracted at 19.5 degrees. And what we have here, this faint line, is the reflected ray. When an incident light gets to a surface, depending on the intensity of light and the materials involved, part of the ray of light will be refracted, while some will be reflected back to the surface. Okay, however, by the time you sum up these two, both the refracted and the incident, you will get the total of the intensity of the incident ray of light. Okay, so we can actually measure the intensity. We have an intensity meter here. Okay, so I pick my intensity meter to measure the intensity of my my refracted ray. Okay, I have 94.22%. okay, then coming over here, what do I have? 5.78. So if you sum up the intensity of the refracted and the reflected ray, it will give me the 100% of the incident ray. I repeat. Now, let me remove my intensity meter. Okay, this incident light, when it comes to this surface, two things happen to the incident light that is coming. Okay, part of it is reflected back to the same medium where it's coming from, which is air. And if you can see, the incident angle is the same thing as the what? Reflected angle. Okay, part of this, and the percentage that refracted is just 5.78%. okay, then the medium, which is glass down here, okay, this refracted light has an intensity of 94.22%, meaning if you sum up the intensity of the reflected and the refracted, we have 100%, which is equal to the incident the intensity of the incident ray of light. Okay, so that is all about that. We can as well get a protractor to measure the angle instead of having it being displayed by the simulation app. Okay, So that can also be measured manually using this protractor. Okay, and we can as well also come and check the speed of this incident ray, and then we can check the speed of this as well as the speed of this. Okay, so that's basically what we have there. Now, another important part that we should take note of is this. We can as well also vary the wavelength of the incident ray, and as that changes also, that also affects different parts of this reflected and refracted rays of light. Okay, another experiment can also be set up by simply varying. While this angle of incidence is constant, we can begin to vary this and then measure the intensity. Okay, take a look at this. As the ray of light, as the wavelength changes, we can also see changes in intensity. So another experiment can also be set up to look at the relationship that exists between wavelength and the intensity of light using this same simulation app. And then lastly, another part that can also be done here is to make use of different material. What actually happened when I'm moving from air this time around to water? Okay, do I have the same incident and refracted angle as to when I'm moving from air to glass? Okay, we can as well also check if you're moving from air to air, what happened? Of course, nothing changes. The incident angle is equal to the refracted angle because nothing changes between the two medium. We can also choose an arbitrary one whereby we are trying to determine what will be our N. Okay, an arbitrary material. Okay, so in this case, my arbitrary material, if I incident an angle 30 and I'm getting a refracted angle of 12. Okay, by Snell's law, I know refractive index is equal to sine of incident angle divided by sine of refracted angle. So meaning I can compute my N, which is refractive index, by simply taking the sine of 30 divided by sine of 12. If I choose another mystery, I can also do the same thing and get that. And then custom, this time around you can even go ahead and vary the refractive index. Okay, and begin to see how does it change if the incident angle is kept constant and you begin to vary the refractive index of the material. What happened to the refracted angle? These are ways by which several experiments can be set up using the simulation app, and this can foster learning for students, especially in Africa where some of the material for physical performance of this experiment might not be available. Thank you. My name is Dr. A.S. Olayinka.